Okay, off we go. So here's where we were last time. We were, this is where we're picking up from last time. Previously, we've been talking about path independence, various cool things about path independence. So here we're going to consider a question. The question is, how do I know if a vector field is a gradient? Sure is nice to know if a vector field's a gradient. For one thing, if you know the vector field is a gradient, that makes it seem like it might be reasonable to put in the effort to try to find the anti-gradient, which of course is very useful, fundamental theorem and all that. Also, if you know that a vector field is a gradient, then you also know that it's path independent, and you also know that all circulations are zero. There's just tremendous amount of information that comes for free if you know that a vector field is a gradient. So how do we decide? Roughly speaking, we're going to form what's called I believe the book, and I like this term, calls a local test, which is this right here. The local test says, if you want to know if your vector field is a gradient, compute the curl, see if you get zero. Simple as that. And so we call this a local test because curl is something that you compute and you evaluate it at individual points, right? It's something that you can test 1 point at a time. Not so much with the anti-gradient question. You need to find a single anti-gradient that works everywhere all at once. Right, so it's arguably a much more challenging question this global question of is there a global anti-gradient. Much easier to ask the question, hey, what can I compute just 1 point at a time? So really nice test. How do we know it's true? And there's a lovely argument for this. Now keep in mind we've already established that these three conditions are equivalent. Now of course this does require a regularity condition we need for the vector field to be C1. That means not just continuous, not just differentiable. Continuously differentiable. The derivative has to be continuous, right? So stronger condition. And it's got to be on the entirety of R2. Right? You can't have little singularities, little holes where, the vector field's not defined at that 1 point. No, nothing of the sort. No, not okay, not good enough. Okay, so that said, here's the cool argument. And it's just to notice that what we have here is a circulation, and Green's theorem allows us to compute circulations with a double integral of curl. And so this, one of our three equivalent conditions over here, circulations all being zero, turns into double integrals of the curl all being zero. Okay, fine. So what? Who cares? What does that buy us? Well, here's what that buys us. This is actually quite a bit that it buys us. Let's just entertain the question of what could this function be? Right? What could a function be? If you know that all of the double integrals are equal to zero for any domain, whatever domain you pick, any domain at all, what could that integrand possibly be? How many integrands can you think of? And by the way, continuous. Right? Continuous integrands. How many continuous functions can you think of whose double integrals are zero everywhere? And no surprise, there is only one such function. That function is the function that's exclusively zero. Okay, so that's the argument. Now, I made the argument in this direction, but it turns around just fine. So this is a double implication. This is a if and only if. This is an equivalence. Now, again, conditions. You got to be really careful with conditions, right? This is assuming the vector field is at least C1. In other words, a nice vector field. Okay. All right. So, let's talk about these conditions just a little bit more. There's a nasty little business here. I'll remind you that we are currently sailing pleasantly over some very deep water. And so you got to be really careful. Bad things happen if you don't have the safety net of these conditions. So when those conditions are satisfied, yes, these are equivalent. and these are equivalent, and of course it follows, but it's still worth saying these are equivalent. So what that means is, if the curl is 0, then it's a gradient and it's path independent. It also means if the curl is not exclusively 0, then it's not a gradient and the vector field is not path independent. So that's what we mean by equivalence, right? These all go hand in hand. If you take away this condition, all of these equivalences go away. And there are various different possibilities, and again, different course would talk through some of, what might these look like. But in particular, you could have a vector field where the curl is 0, but it's not path independent. And you can have, in a different way, a path independent vector field, but the curl isn't 0 exclusively. And all sorts of failures of these equivalences. Now, that's not to say that none of these conditions can happen. It just simply says that we cannot assume that they're equivalent. Right? So this is about the equivalence of these three conditions. So those conditions, very important. Okay. Now let's talk about terminology a little bit. What are we going to call a vector field whose curl is 0? Let's think about what would be a reasonable name to refer to a vector field whose curl is 0. And I think the following is extremely reasonable. After all, curl describes, and we talked about this at length a while ago, it describes the rotational aspect of the fluid in some sense. Right? To what extent you drop a leaf on the surface, the leaf starts to move, of course, but it also starts to rotate. Curl tells you how it rotates. If that's 0, then there is none of that rotational aspect. And so you might think non-rotational or unrotational. Apparently the grammatically preferred term is irrotational. So I gather. So anyway, I think this term makes loads of sense. When the curl is 0, irrotational. Extremely natural terminology. I love it. It gets right to the point. Geometrically, how am I supposed to think of this vector field if curl is 0? There's no rotations. Okay. So irrotational, great word. Okay, what else have we got? We've got irrotational. We've got path independent. We've got gradient. Right? So now let's just take a quick moment to recognize, in the case where you have this nice condition, where it is a C1 vector field on R2, we've got a collection of vector fields that satisfy these three different properties. But said differently, we've got a collection of vector fields that we can call by any of three different names. Right? So gradient, path independent, irrotation. It's all talking about the same vector fields. And so I ask rhetorically, why do we need a fourth? Right? It just always seems unnecessary to me to say. And by the way, sometimes we will call these conservative, right? And that's the more common term. It's a more common term. You're probably going to hear the word conservative more often. It just means path independent, aka a gradient, aka irrotational, assuming the regularity. So anyway, I tend not to use the word conservative. I like to say gradient or path independent, depending on which of these conditions I'm actually interested in at the time. Okay, so punchline. If you want to know if something's a gradient, aka if it's path independent, aka if all the circulations are 0, no problem. Here's your local test. Compute curl, see if you get 0. Okay. Side note, this is in 2 dimensions. There is an equivalent, there is an analogous test in 3 dimensions. This 2-dimensional test, there is an analogous 3-dimensional test. And the test, again, for whether you have a gradient, for whether it's path independent, for whether the circulations are all definitely 0, the test is 3-dimensional curl. Del cross, right? Not to be confused with 2-dimensional curl. These are highly analogous, but nevertheless importantly different operators, right? I mean, three-dimensional curl is a vector field. Two-dimensional curl is a scalar-valued function. They're they're qualitatively different critters. They are functionally different in terms of how we incorporate them into the algebra. You'll see more of that when we finish covering Stokes' theorem in a couple weeks. But anyway, they go by the same name, curl. So anyway, same test, and that's kind of nice. You take the curl, you see if it's zero. Okay. All right. Now, I'm not going to prove this latter theorem yet because the latter theorem, where I used Green's theorem, I need to use a different theorem that we haven't covered yet. So I can't do that proof yet. But let me just say, for your curiosity, a little bit of foreshadowing, we will soon have a theorem that's going to go right there, that's going to perform the role, exactly the role that Green's theorem is playing right there. And it's all going to fit, it's all going to make sense, and we're just a couple weeks away from that. So anyway, that's a little foreshadowing. Okay, so let's do it. Let's get one under our belts. Here is a vector field. I would like to know, is it a gradient? By the way, why would I want to know if it's a gradient? Let's just remind ourselves. Well, if I'm interested in computing a line integral, and if I know the vector field of the gradient, then I can just find the anti-gradient. We'll talk about how to do that in a moment. But if you can then find the anti-gradient, you can use the fundamental theorem of line integrals, which is awesome, right? So knowing whether it is or is not a gradient, very valuable information. Okay, so we play the game. Compute the curl. Let's see if it's zero. All right, so off we go into computing the curl. You'll notice the curl, as I discussed previously, is a vector field. It has three coordinate functions. The question is whether all three coordinate functions are zero. Right? So importantly, I need for the curl as a whole, the curl as a vector field, to be exclusively identically zero, which means I need all coordinates to be zero. And here's the cool thing about it. I don't even have to compute all three coordinates then, because I compute the first coordinate, I see that that's not zero, and I instantly conclude, well, I've got one non-zero coordinate, couldn't possibly be all zeros, therefore I don't even need to compute the remainder. Does that make sense to everybody? Right, now this is a one-way trick. If I had gotten zero for the first coordinate, I would still have to continue, because again, the question is not whether there is a zero coordinate. The question is, are all three definitely zero? So one-way little trick there. How we doing? Everybody happy? Everybody see how to use this test? So, by the way, let me point out what the win is here. There's a temptation to say that this is bad news, but I say that we just saved ourselves some effort, because now I know that this is not a gradient. If it is not a gradient, that means that there is no anti-gradient. And if I know that there is no anti-gradient, I'm not going to waste my time trying to find the anti-gradient. Right? And, okay, fabulous, because golly, I could imagine I maybe would have spent a fair amount of time looking for this awesome anti-gradient. That would be totally sweet to be able to work with. And nope, I'm not going to waste my time. I know it doesn't exist. That's a wild goose chase. Don't bother. Okay. All right, moving along. Okay, two-dimensional example, back to 2 dimensions. And let's see, here is a vector field. By the way, we've drawn this vector field before. This is the stirred pot, I like to call it. So it's a little counterclockwise rotation. Is this a gradient? Well, we apply the local test. We compute the curl. It is not zero. And so this is not a gradient. And again, don't bother trying to find an anti-gradient. There isn't one. Wild goose chase. Everybody good so far? Okay, now, by the way, just a little bit of geometric satisfaction, I hope. Kind of couldn't possibly be a gradient. I mean, we know what this thing looks like. It looks like this. If that were a gradient, that would mean that all of these field vectors point uphill. That would mean that as I travel around in a circle, I would be continually walking uphill, 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 uphill until I come right back to where I started. That's nonsense. And by the way, it's nonsense that we've previously seen. That's exactly this scenario here, right, with the Escher stairs. So we've already refuted this. So we kind of, I'm glad that we did the algebra, but now we have conclusive, incontrovertible evidence that this is not a gradient. But let's face it, that's the answer that we kind of knew had to happen. Said differently, another equivalent condition, remember, path independence, another equivalent condition of path independence is that all circulations are zero. Well, I see some pretty obvious circulation there. So the fact that there's circulation, again, I'm pretty sure, right, that this was going to work out as it did. How do y'all feel about that? Is that intuition, kind of geometric intuition track with y'all? Okay. Cool. Moving along. Okay, so this next little discussion, this is something I'm going to say kind of mine. This is not in the book that I recall seeing. In fact, most multivariable calculus books don't have something like this. By the way, this, what I'm calling the strategic diagram for R2, is also available. Did I remember to do this? I had intended to put this PDF file in the Google folder that we're using in the absence of the website being... Oh, by the way, I've heard good news about the website. Apparently there is optimism that the website will be coming back in the next day or two, maybe. Then again, there was optimism on Friday. They would have come back over the weekend. So, I don't know. Who knows? We'll see. But anyway, fingers crossed, maybe the website will be back soon. But I'm coin flip confident I may have already put this file into the Google folder. If I did not, then I appreciate any reminders or nudges that y'all might be willing to give me. So diagram.pdf, and let's see here. Here it is. It's this file right here. It's kind of a more detailed diagram. So let me tell you where this comes from. I've mentioned previously that there is a powerful and sophisticated take on all this vector calculus. And it uses something called differential forms, right? And I've made some sort of casual references to differential forms. Very powerful idea, very powerful tools. The way you use differential forms is you create something called chain complexes and co-chain complexes and blah, blah, blah. A bunch of, there's a lot that needs to get done on that. So again, I can't really show you the full story. It's just too much. What I've got in this diagram is I've taken all of the abstraction and formalism and rigor out of it, boiled off all of that stuff, and left just what I'm going to call the bones, the structure of what's going on. And if you do, this is kind of what you're left with. So now I understand that this is not therefore a proof of anything, because I'm just making an assertion that this comes from these very powerful, very sophisticated ideas. So if you're willing to trust me on that, right, then I think what you're going to find is that this is an extremely useful diagram to have in your heads. And by the way, whenever I think about vector calculus, I'm always thinking about it in the context of this diagram. I guess I should say that diagram and its three-dimensional analog, which is this. Now, we haven't talked about all of the objects on this diagram yet, right? So we have yet to discuss whatever that critter is. That we don't even know what that means. We've barely discussed curl and divergence. In 3 dimensions, I certainly haven't given you much reason to believe that those formulas that we wrote down in 3 dimensions back in chapter 3, that they do anything. And we certainly haven't discussed these theorems yet, right? So most of what's on the right-hand side we haven't even talked about. So what I'm about to show you, consider this a preview. Consider this a way to help yourself have a organized kind of approach as we start by the way, later today, as we start going into 3 dimensions and start thinking about these things here. So the big idea is that this diagram has just a ton of patterns in it. And why don't I come back up here to 2 dimensions first, because we already understand everything on this diagram. And here are a couple of patterns. First of all, let's talk about Green's theorem. Green's theorem says that if I have a vector field and if I compute the curl, by the way, don't forget, GRN is one of my little notations. I'm kind of in the process of phasing it out, right? But it's an alternative notation for curl that I kind of made up. But anyway, if you have a vector field and you compute the curl, if you have a 2-dimensional region and you look at its boundary curve, then the vector line integral of your original vector field on that boundary curve and the double integral of Green's curl on your original 2-dimensional region will be equal. That's what Green's theorem says. And again, regularity conditions, blah, 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 right? But so now just to streamline that, the way I like to represent that here on the diagram is like that. So there's this pattern of what you do to what objects that are where in this diagram, and this is what Green's theorem looks like when you do that. Now, let's think through, same process. On the diagram again, for the fundamental theorem of line integrals. By the way, let's quick moment to just recognize fundamental theorem of line integrals, totally different theorem. It's got nothing to do with areas. There is no curl involved, right? It's just different, completely different. It involves gradient, not curl. It's a totally different theorem geometrically. But check out the pattern. If you have a function and you compute its gradient, if you have a curve and you look at its boundary, which of course is just its endpoints. It's got a starting point and it's got an ending point. And if you evaluate the original function on those endpoints, like so, and if you take the line integral of that gradient over the original curve, like so, then those results are equal. Or said differently, we might abbreviate that like so. So I think, just my opinion, right? But I think that's a jaw dropper. Right? That we have these 2 geometrically totally different theorems, and yet, oh my God, the pattern's the same. It's the exact same pattern. How could that be? Right? It's just really surprising. And by the way, this pattern continues. Down here in 3 dimensions, we already know the 3-dimensional fundamental theorem of line integrals. In fact, it's basically the same theorem. I claim, and many details to come, and we've got a lot of stuff we need to develop, but when it comes time to talk about Gauss's divergence theorem, here's the pattern. If you take the divergence, if you look at the boundary surface, and if you compute whatever that thing is, and you compute this, then you get the same thing. It's the exact same pattern. The Gauss's divergence theorem is morally equivalent in this sense to the fundamental theorem of line integrals, and it's morally equivalent to Green's theorem, just adapted appropriately to the geometry of the circumstance. And then, by the way, same for Stokes's curl theorem. If you follow the pattern, you get the same thing again. So this is really cool information. So said differently, rather than thinking of these theorems as arguably 5 different theorems with 5 different geometries, what you have here is an opportunity to view this as a single pattern. Right? If you just use the diagram, trust the diagram, arrange the various players exactly the way that I have arranged them here, which, by the way, again, it's not like I did anything particularly creative there. This is just what stuff looks like when you're doing differential forms and chain complex, co-chain complexes, blah, blah, blah. If you just trust the diagram, you don't have 5 separate theorems to understand. You have one pattern to understand. And that's a big help. Now, side note, yeah, of course, I'm overstating it a little bit. Obviously, you should be thinking about the geometry of each individual circumstance as well, of course. But having this framework, but it's one pattern, and all you got to do is keep track of what's where, and this does a lot of the memorizing for you, for one thing, right? And other nice advantages. Okay, so that's the first thing I want to point out. Now let's also talk about, let's see here, let's go up to 2 dimensions again. Let's talk about the special vector fields. We've talked about the special vector fields before, certain vector fields. We were just talking about how if it's a gradient of something, regularity conditions assumed, of course, that means that curl would have to be 0. And it also means path independence, namely, here's the way I like to represent path independence on the diagram. If I have 2 curves that start and end at the same points, namely they have the same boundaries, right? Then they give you the same value of the line integral. So that's just how I like to draw path independence on this diagram. Okay, so that's what these 3 equivalent conditions look like in this situation. Hopefully no surprise. Something totally analogous happens in 3 dimensions. Now it's 3-dimensional curl instead of 2-dimensional curl, but path independence is basically the same idea, and being a gradient is basically the same idea, right? So, okay, fine. So maybe not that surprising that it looks exactly the same in 3 dimensions, but here's the weird one. You've got to be kidding me. Not only does it look the same there, it also looks the same over here. That's crazy. Right now, again, totally different geometry. But what this is telling us, what I'm claiming here, and again, we're going to go through and talk about a lot of these details. So, chapter 7, there's a lot to talk about, right? But be on the lookout. If a vector field is a curl of something, then its divergence is 0 and vice versa. If the divergence is 0, divergence being 0 is a test for whether or not that vector field is a curl of something. And by the way, we can also kind of anticipate this new property that we've got colored in orange here, which seems to suggest that if I have 2 surfaces, I guess, apparently, if I have 2 surfaces that have the same boundary curve, then those for the special vector field will give me the same value of whatever that is, which again we haven't talked about yet, right? Something called a vector surface integral, but anyway, that's to come. So there is a new concept on its way that you can almost kind of anticipate because of this shockingly consistent pattern. Okay. So again, another major advantage of thinking about things in the context of this diagram. By the way, let me make one last, maybe not last, but one other observation. Let's go back over to here. You know what? Now let me go back up to 2 dimensions. How did I prove this local test? Well, Green's theorem played a big role, right? How did I prove the relationship that we showed between path independence and being a gradient? Well, fundamental theorem of line integrals was the thing that made that work. Right? Okay, so based on the pattern, we might speculate. Now this is purely shameless speculation that I'm about to throw on you. Well, if the pattern is so great, wouldn't that kind of suggest maybe that, let's see here, let me see if I can highlight all of that. Let's go down here. And then by the way, let's come, oh, can I do it? Oh, tricky. Okay. Man. Boy, it's hard to get that on there. Highlighted too much. Okay, there you go. Good enough. Shameless, baseless speculation. If the pattern holds, that would kind of suggest that, well, apparently this thing called Gauss's divergence theorem that we haven't even seen yet, apparently Gauss's divergence theorem is going to help us understand why divergence relates to a vector field being a curl. And you know what? That's going to turn out to be exactly right. The pattern continues in which tools are useful for what kind of arguments. Also, so as the pattern would suggest, yeah, it's going to turn out. And by the way, you can use this yourself when you're trying to figure out, oh, how would I make the argument about blah, blah, blah? Look to a different context. Look to what's useful in that different context. Notice the pattern and extrapolate. And, yep, probably going to work. So not only is Gauss's divergence theorem going to help us understand the local test of divergence, resolving the question of whether something's a curl. Furthermore, this thing, let's see, it's called Stokes's curl theorem, apparently, right? Well, that's going to be the thing that's going to help us understand the relationship between the green and the orange. And by the way, that orange is going to be something called surface independence. And again, with a lot to talk about, and we don't even know what that is yet, but that will be how that connection works too. So my point here is that the patterns are extensive. And the fact that those patterns are extensive are an opportunity for y'all to kind of almost sort of cheat. It's like having a hint book of, okay, whatever the pattern is here, just look over to the lower dimensional case, see how that works, extrapolate to the higher dimension. It's a way of guiding yourself to good ideas. Okay. All righty. Okay, so I think that's really cool stuff, and moving along now, finding antigradients. Why don't I go ahead and step this up? There we go. Okay, so we've talked about the fundamental theorem of line integrals. Cool theorem. All you need is the antigradient, and you may have noticed I've been pulling antigradients out of thin air. I have yet to show you how to find an antigradient. Okay, so let's talk about how to do that. It's actually a pretty natural method, ultimately no big deal. But here's the thing. If you have a vector field and if it is a gradient, well, the vector field has coordinates. Gradients are computed by a formula that has coordinates. And that would mean that these have to be those. Namely, these three equations. Okay. So we've got three equations to look at. I need to know how to find this f, whose partials are what they sort of have to be. And now let me just make the observation that those three equations are not that different from these three equations. It's just sort of grammatically backwards. So on the left, for example, top left there, we have the x partial of f is p. Top right, we have f is the x antipartial of p. It's the same statement, morally. I mean, not that good. Both of them say the same thing, that there's a derivative relationship from one to the other. It's just that one of them says it backwards. So it's just like saying if capital F is the antiderivative of little f, then the derivative of capital F is little f. It's just grammar. Now, there's this business about integration constants. And it's tempting to say, oh yeah, anytime you have an integral, oh yeah, don't forget to say plus c. Let's revisit that a little bit. Wait a minute, why do we just say plus c? What gives us the right to just throw in constants for, wait, why now? You're free, you can just add constants. Keep in mind, the whole idea of adding a constant is that what you're actually interested in is looking at the x partial and being able to have arranged what that x partial is. And the whole point to the constant is that constant, when you take the x partial, you get 0. Right? That's why we add constants when we do antiderivatives, because it doesn't matter. When you take the derivative, it disappears. So the twist in this case is that more than just constants have this feature. More than just constants have the property that the x partial makes it disappear. And if you think it through, I think this is a nice little thought exercise, but okay, well, what are the expressions that when you take the x partial, poof, disappear in a puff of smoke? And the answer is not just constants, but any function that doesn't have any x's in it. Right? And so these are what we call, and I think this terminology makes loads of sense, this is what we call a partial constant. Right? It's in terms of partials with respect to x, this behaves like a constant. Okay, so weirdly though, no longer just constants. Now they are functions. They're just functions that can't have any particular variables in them. So again, no x's in here, no y's in there, and no z's in there. Okay, so this is what we've, excuse me, this is what we've got then. If I want to know, is there an f, is there an antigradient, I need for that f to equal to all three of these things. And next observation, if f is equal to all three of these things, then all three of these things need to equal to each other. And that's going to be the goal. That's how we're going to actually get stuff done on this. We're going to write down these three expressions and we're going to ask, can I make them all equal to each other? And don't forget, I get to pick these partial constants. I get to pick them to be whatever I want. Okay, so that's the game. It is, I think of it as a kind of a little game, and here's an instance of the game. Here's the vector field, and I want to know, is there an antigradient, as usual, and using the formulas from the previous page, this is the P. So I need F to be the x antipartial of P, and then likewise that. I'm going to look at the y antipartial of that, and here's my R, and I need the z antipartial of that. And y'all are good at calculus. You can do these antiderivatives here, right? No big deal. And don't forget to add in your partial constants. Okay, fine. Now, again, what I need is for all three of these things to equal to each other. Don't make the mistake of giving up too soon. I know that at a casual glance, they don't appear to be the same. But don't forget, we get to pick these partial constant functions to be whatever we want them to be, right? Think creatively, right? And so, for example, I mean, part of my problem, right? Part of the reason that these functions don't look the same is because, look, there's an x squared y and there's an x squared y, but I don't see any x squared y down here, and I'm not happy about the fact that, well, apparently they're different because there is no x squared y. But, you know what? I am perfectly within my rights to make C3 x squared y. And now I've got the same term in all three expressions. And things are looking better. Okay, so likewise, got an xz, not happy about the fact that there's no xz. Oh, wait, that C2 is allowed to be xz. So how about we just do that? And now again, consistency. And then lastly, I've got a minus yz squared and a minus yz squared. How about I just make that minus yz squared? And now check it out. all three of these purple expressions are green plus blue plus orange. Indeed, these are all equal to the same thing, namely that. So we win the game. Everybody see how that works? And by the way, just for the confirmation that this actually is doing what we claim that it's doing, I think it's a nice exercise. I encourage you to do the following: to actually take this and take its gradient. When you take the gradient, you're going to get exactly f, as desired. So we have successfully found that anti-gradient. Okay, everybody see the process? Okay. Cool. Doesn't always work. Shouldn't always work, right? Let me remind you, not everything is a gradient, right? In fact, we have this test to even decide if something is a gradient. This has got to be true, and of course, not every vector field is going to have curl equal to 0, right? So there are some vector fields, like this one, that are not a gradient. And if it is not a gradient, again, this is not a gradient, when we look for an anti-gradient, we better not find one. Right? That'd be bad, right? If our little anti-gradient game produced anti-gradients that aren't anti-gradients, that would be bad. So let's entertain. How does this go wrong? Here is that exact vector field. We're going to play the game. What does it look like when the game fails? Well, I do the same usual process, right? We take the antiderivatives. Again, y'all can do that. Don't forget about your partial constants, right? This is any function that doesn't have x's in it. This is any function that doesn't have y's in it. And now, let's play the game. Can you think of a function of only y and another function of only x that makes this equal to this? And no, you can't. And if you don't believe me, try. Right? You're going to try, and you're going to keep running up into a brick wall. It just won't work, and so there is no anti-gradient. So anyway, this is what it looks like when you're trying to find an anti-gradient that doesn't exist. And by the way, hopefully you'll never actually encounter that brick wall, because when you would have encountered that brick wall, maybe you will have had the foresight to just eyeball glance compute curl, and once you notice that it's not 0, then you know that this whole thing was going to fail. So you don't have to actually go through and experience the failure. Does that make sense, everybody? All right. Okay, moving along. We're done with chapter 6 now. Moving into chapter 7. Chapter 6 was mostly about vector calculus in 2 dimensions. Green's theorem was our big theorem, right? Green's theorem exclusive to 2 dimensions. Fundamental theorem of line integrals was one of our other big theorems, and most of the examples that we taught, we kind of were mostly focused on 2 dimensions. Okay. So we're going to now move on to 3 dimensions, and roughly speaking, chapter 7 is about vector calculus in 3 dimensions. And as I've already kind of referred to when we were doing the diagram, we've got some machinery we have to build up. There's some constructions we need to create, and some observations, connections that need to be made. So we've got some groundwork to lay. And by the way, don't forget, one of the big players in chapter 6 is we define something called a vector line integral. That's involved in the fundamental theorem. It's involved in Green's theorem. Right? Vector line integrals are a big deal. And how did we define vector line integrals? Well, by parametrizing. We pull back through parameterizations. So I hope it'll come as no surprise when we try to do something like that for surfaces. we're going to need to parameterize surfaces. So that's where we're going to start here. We're going to talk about parametric surfaces. Here's our first example of a parametric surface. Let's see here. By the way, I will remind you with a quick flashback to chapter 5. Chapter 1. Section 1.5. And by the way, this is on page 26 of the lecture notes, right? So that's how long ago. This was like way long time ago, like probably like the third day of class or something. And we made this observation that this is another way to describe a plane. And we talked about planes where you can write down the equation of the plane. And then we talked about lines, and you can have, in some cases, an equation of a line. Some cases, it's symmetric equations of a line. And parameterized lines. And while we were doing all that stuff, make the observation that, well, you can also parameterize the plane. And the big idea is that if you want to generate points on the plane, well, pick some starting point that is known to be in the plane, have a couple of vectors that you know to be parallel to the plane, and then, let's see here, let me use dark green. You have the ability to just pick different scalar multiples of those parallel vectors, and when you add dark blue plus dark green, as indicated there, then pick your scalar multiples appropriately. But that can get you anywhere you want to get in the plane. Right? You can get to any purple point in the plane from that base point dark blue in the plane by going some multiple of V plus some multiple of W. All right, and now I'm just going to point out that those multiples, S and T, those are your parameters. And so this is why we call this a parameterization, because every point in the plane that we're generating by this expression is generated by choosing values of those two parameters. And that's parameterization. Okay. So again, old news, something we did a long time ago. And by the way, I'm well aware that this class is super fast, and we've covered a ton of material. Right? It's an outrageous workload, and I totally get that. So I know it's been a long time since we did this, and so you might want to rewind and re-listen to some of this stuff again if you feel you could benefit from that. Okay, so yeah. Here's that formula again, just written a little bit differently, written with the name of a function recognized as R2 to R3. And that's just what we did in section 1.3. Okay. All right. Now, there's a little bit of a cost when you're talking about parametric surfaces. Yeah, it's a lot like parametric curves. It's not exactly the same as parametric curves, but pretty similar. There are parameters, and you're generating points. It's highly analogous. Here's one of the big differences. Because we have two parameters, I can't say that the parameter represents time. Right? At least not in a particularly intuitively relatable way. If you only have the one parameter, yeah, that one parameter, call it time. We have one notion of time. We have one parameter. Go ahead. If there's two of them, they need to be different. We don't have in our brains this idea of having two independent notions of time. I don't know. I think that'd be a pretty weird science fiction movie. I'd probably watch that movie. I probably wouldn't understand that movie, though. It's not a particularly helpful metaphor. So we have to kind of jettison this idea of thinking of the parameters as being time. But, oh well, everything else is pretty analogous. Okay. How else can we parameterize surfaces? Planes are tip of the iceberg. Okay, next. My favorite surface parameterization technique is the graph parameterization. You may remember that term. We talked about the graph parameterization of curves back when we were looking at parameterizing curves. Again, way back like first day of class, one of the first things we did is talk about parameterizing curves. And I gave you all a couple of different methods. And again, this was my favorite. And I claim this is basically the same idea. If you have a graph, whatever your input variables are to that function, those input variables, let them be your parameters. Just like the lower dimensional version that we talked about back in chapter 1. There was only one input variable, and it became the one parameter. Here there are two input variables. They become the two parameters, S and T. All right, so let's see this in action. Here's an equation. More to the point, this is a graph, right? Because I've got Z solved for as a function of X and Y. Now I'm going to follow the rule. I'm going to let X and Y be S and T. Namely, my input variables are my parameters. And, well, that kind of does it, because if I take those formulas for X and Y, plug in, I kind of, wrong color. I kind of have to then let Z be S squared plus T squared. And as desired, notice I have now position, with the colors, position as a function of two parameters. And that is a parameterization. So it is a lovely technique. It applies fairly often. Not always. Not even, I hesitate even to say usually. But pretty often, you can parameterize stuff by this easily implemented method. I mean, the method tells you what to pick your parameters to be. Everything else is just unavoidable, and you just plug in. It's very follow your nose. And again, it works nicely very often. So, fabulous technique. By the way, nothing magic about the alphabet. It doesn't have to be Z specifically. It can be any variable solved for in terms of the others. So here, for example, let's look at this equation here. Doesn't even look like a graph. I could try to turn it into a graph. Could try to solve for Z. Not going to work. Right? You can't solve for Z algebraically. This is not algebra friendly. But even though I can't solve for Z, I can solve for Y. So in that sense, yes, I have a graph. Y is a function of X and Z. So again, my input variables X and Z, I let those be my parameters, just following the rule. And with that said, I kind of have to choose Y then to be this expression, and boom, done. We win. Parameterization. Everybody good? So any variable you can solve for in terms of the other variables, all good, fine. Just follow the pattern. By the way, furthermore, it doesn't even have to be rectangular. It can be any variable in any coordinate system. Now, when you create a parameterization, typically we view a parameterization as being a rectangular position as functions of parameters. So I do need to have the conversion formulas in there. That you do kind of have to do. But once you write down those conversion formulas, again, it's really just a matter of plugging in. So for example, here I have what you might call a spherical graph. I have one of these spherical variables solved for in terms of the other two. Here I have rho as a function of phi and theta. By the way, some people get uncomfortable when I claim that this is a function of phi and theta, because they're like, where's the theta? Right? It's a really easy function of theta in that its dependence on theta is don't worry about it. Right? That's still a function. Right? By the way, let's think about a single variable analog of this. If I want to talk about y as being a function of x, if y is x squared, cool. If y is x to the 10th, fine. If y is e to the x, cool. If y is 3, yeah, Still a function. It's just an easy function, right? So the x doesn't have to be in there, and likewise the theta doesn't have to be in here. So nothing to worry about that you can't see the thetas. The point is I've solved for rho. Having done that, again, plug it in. You don't really hardly have any choice in the matter. Those rho's become cosine phi, and as desired, I have position as a function of two parameters, phi and theta. How we doing? Everybody good? By the way, I do want to talk about a confusion of variables point. Some students might complain that, hey, wait a minute, but back here you renamed the input variables with other names. Why didn't I rename phi and theta here? And that's a good question. It's a valid gripe. The reason I did is because here I would have had a confusion of variables problem otherwise. If I had left x as x, and if I had left z as z, oh gosh, I've got a lot of, okay, well anyway. If I had left everything in terms of x and z, then notice, oh, and then this is x, and this is z, then I would have x and z being both input variables and output variables. And that's disturbing, right? That should make you uncomfortable. Anytime you create an opportunity that, oh gosh, this might be a confusion of variables, I encourage you to be a little bit uncomfortable with that. And so I sidestep that problem by just saying, you know what, sure, I'll just rename the inputs. Easy to do. Problem avoided. Now S and T are the inputs, X, Y, and Z are the outputs. There's no confusion of variables, nothing to worry about. Okay. In this situation here, it wasn't a problem in the first place. Phi and theta were never output variables. So it's okay for them to be input variables. There is no confusion of variables concern at all. Okay, so if you want to rename phi and theta as S and T, I suppose you may, but it strikes me as unnecessary and, by the way, arguably counterproductive, because we know what phi and theta are. We know what they look like. We have geometric intuition for them, and when there's good geometric intuition to be had, it's nice for it to be obvious. So I think it's better just to leave the phi and the theta. Okay, how are we doing? Is everybody happy? Is everybody following? Okay, all right. Okay, this next example, sadly, well, sad for me, less sad for y'all. Optional. I have spent time doing this in the past. I think this is a neat example, but this technique, this category of strategies here that this example represents, I have to confess, it doesn't come up very often when you're parameterizing surfaces. So I am going to call this optional. For whatever it's worth, I hope you all remember way back when we did the parametric curves that came from the bicycle reflector. Y'all remember the bicycle tire and the reflector makes this herky-jerky pattern like that, and how do we parameterize that? And what we did is we took this very weird curve, and we realized that all it is you just have to keep track of where the axle is. That was easy. And then you have to keep track of how the wheel is rotating, and that was pretty straightforward. There's a little bit of trig, and you got to be careful about notation and stuff, but basically pretty straightforward. This is kind of an analog of that, of taking a hard problem and turning it into a sum of simpler problems. And in this case, what we have, just in case you decide you want to look through this stuff, we have a surface S for which it's easy to create points because it's a graph. We use the graph parameterization. And then the idea is we have these little hairs sticking out of length 1, and they stick out perpendicularly to that surface. And so you just have to generate a normal vector and make an argument down here. about graphs being level sets of a different function. I hope y'all remember that trick. Really cool trick. If you have a graph, it's also a level set of something else. Once you have it as a level set, you know the gradient is orthogonal. Flashbacks to chapter 2. And then this weird surface, H. How do I generate points on that weird surface? Well, no big deal. At that point, it's green plus orange. If I can squeeze this all in. Yeah. So, green plus orange, pretty obviously, missed the color. Pretty clearly green plus orange gives you purple. So, okay, I just wanted to hit some highlights. It's not that bad, but it's also not something that comes up that often, so I don't want to spend any serious class time. Okay. This next one does come up a lot. This is a really important method. I think this is one of the more underappreciated methods for parameterizing surfaces. I think this is a really good one. I've used this one myself many times, and again, an undergraduate physics major is different from an engineering major, I know, but it's not that different. So I think y'all will find this to be really, really useful. So let's ask the question, how are we going to parameterize this torus? And just a reminder, the word torus just means the surface of a donut, like so. Okay. How to parameterize this? The big trick of this method is to create a new coordinate system. Now, create is a big word, right? That's a big tent. I get to make whatever coordinate system I want. It's entirely at my discretion how to create this coordinate system. So with that flexibility, an important idea is make up a coordinate system that's natural to the situation you're looking at, right? So let's imagine that we were living on a planet that was shaped like this. It would be weird, right? But I've heard weirder thoughts. If we had a planet that was shaped like this, what would be like the longitude and latitude, right? How would that have been set up? And now longitude and latitude are set up based on the way spheres are shaped, because the surface of the planet we do live on happens to look a lot like a sphere. So longitude and latitude are tailored to that circumstance. We're just going to kind of tailor a different sort of analogous longitude and latitude. Okay, so the way this is going to work, we're going to start by fixing some base point, some sort of starting point, just a reference point, right? How would I describe that location right there with respect to that given reference point? How would I describe that location? Now, again, you get to pick. It's up to you, your choice. Here's what I think makes sense. I think this is natural given the nature of the shape we're looking at. I would say, look, from this dark blue point, you're going to have to rotate what you might call around the dough, around the meaty part of the donut, the doughy part of the donut. You'd have to rotate by some angle. Let's call that T. And then from there, we would have to rotate around the hull. You might say around the z-axis. Going to kind of feel like you're rotating around the hull by some other angle, and we'll call that S. And if you give me a fixed reference point, and if you give me numbers S and T, boom, I know exactly what purple point you're talking about. Does that make sense? Now, notice how this is tailored to the geometry of the surface we're looking at, right? We're looking at the donut. The donut is, just loosely speaking, it's round this way, but it's also kind of round in that other way. Angles are fabulous tools for understanding round things. And so I think this is a pretty hard to beat choice of a coordinate system. All right, is everybody okay with that? All right. I claim it's all over but some details. The big idea of this method is create a coordinate system and then simply write down a formula for the point you're interested in. And so this is a two-step process. I'm going to observe that blue point that we started with. This, that's sort of clear where that is. But this orange point there, I can just write it down as being a sum of that red vector, which is easy to write down, plus, color choices. I'll use dark green, plus this B vector, which is that. Now I'm going to leave the geometry for you all to think through. This is a good exercise, you'll notice, for students to read. Right? So think through the details here. But red plus dark green does give me that orange point, and these two vectors, the red and the dark green vectors, you can write down just with a little trig. Now make sure you can do that, right? So you do have to know trig. Right, you got to be good at trig, and then you also have to understand the geometry of this vector and what does this angle t do, and how does t make that green vector move, and you think through the geometry and the trig. But there is that green vector, and so adding them up gives us p. That orange vector up there. Okay, so that's the first half. Now that's not good enough, right? That's not the whole story. We're interested in actually finding this purple point. To get from the orange to the purple, I'm going to have to figure out how to rotate around the hole, or again, as we said, rotate around the z-axis. How do we rotate around the z-axis? And again, I hope you all remember your linear algebra. Remember, rotations are linear transformations. Linear transformations are matrices. Matrices are understood by their columns, and the columns are the images of the standard basis vectors. Right? So think through that little process, apply that rotation to standard basis vectors. What you're going to find is that this rotation is executed by that matrix right there. Make sure you can do that. If you get stuck, of course, come to office hours. Happy to help. Right? No problem. I want to make sure everybody's good at this. If you're already good at that, if you already get where these columns come from, cool. All good. If you have any questions, come talk to me. We'll talk through it. Okay, and so at this point, it's kind of all over. I've got a formula for that orange point. I've got a formula for the blue rotation, and the point that I want is the rotation of that orange point, both of which I've already computed formulas for, and that leads me to a formula for location on the surface as a function of my new coordinates. S and T, aka I have a parameterization. Everybody see the strategy there? Now, there's a lot of details. Can't emphasize that enough. Of course, a lot of details. Make sure to see the details, think through the details. But the big picture, I created that coordinate system out of free will. Right? I made it up. I made it up in a way that was tailored to the surface I was interested in. But having made up a coordinate system, all I had to do was solve for position in terms of those coordinates, and presto, parameterization. Powerful method. I've used this a million times in physics classes, to parameterize surfaces. Did I see a hand a second ago when I was I thought maybe I saw a hesitant. No? How are we doing? Is everybody happy? Everybody following? Not happy? Do you have a question? Feel free. Okay. All right. April Fools, I guess. Yeah, right. I got my daughter this morning. I told her that when I was her age, I ran away from home and joined the circus. And she bought it. She was a little suspicious, but she kind of bought it for about 30 seconds. Yeah. Okay. Ooh. Okay, moving along. Here's another method, another really good method, and again, I've used this one a million times as well. I think this is really useful for a lot of circumstances. Sometimes you have an existing parameterization, and yet what you want to parameterize is just a little different. So what we're going to talk about is how to take a parameterization you know and deform it just enough as needed to get the parameterization that you're actually interested in finding. Okay, so here's the idea. Let's start with the unit sphere, and you all have seen the unit sphere, of course, a million times. There's the formula. A little bit easier, though, to recognize it in spherical coordinates. And using that spherical formula, that's a graph. It's a spherical graph. I've got rho solved for as a function of phi and theta, a really easy function of phi and theta, but still it's a function of phi and theta. It's perfectly fine. And plugging that in for where rho goes, sure enough, we get a parameterization of the sphere. All right, now that's just a flashback to a method we already talked about. Don't forget, by the way, that when you parameterize something, what you're doing is you're writing down formulas for x, y, and z. And so alternatively, I can think of this as just position, vector, of course, position as a function of phi and theta, or you can think of it instead as 3 separate coordinate formulas. Right, so take your pick. It's the same thing either way, whether you think of this as a vector notation for the parameterization or a coordinate notation for the parameter. It's the same thing. Is everybody cool with that? Everybody happy? Okay, so here's the parameterization that we have. That's what I'm going to call our existing parameterization. And now let's think about how are we going to have to deform that? Well, if what I want, instead of being a sphere, what if I want to parameterize this ellipsoid? Now that's not a sphere. This, what I have in green, absolutely does not parameterize that ellipsoid. It's a totally different surface, right? But it's not that different. We know where ellipsoids come from. Ellipsoids start. It's like imagine that they're born as spheres, and then we just stretch them out a little bit in the 3 different directions, right? They're just stretched out versions of spheres. You can see the stretching happen, by the way. Wrong color. That x in the equation I just replaced with x over a. We know what that does. Flashing back to chapter, whenever we did that, chapter 2, I guess it was. That's just a stretch in the x direction by a factor of a. This is a stretch in the y direction, etc. So the big idea, and I'll have to finish this next time, but the big idea is going to be, okay, if you, in the algebra, replace x with x over a, okay, cool. I can do that in the parameterization also. That's most of the idea. We'll talk about this more later. Y'all have a good one. See you later. See you on Thursday.